In elementary algebra, we are often taught that a continuous line is simply one you can draw without lifting your pencil. In calculus, however, we move past visual intuition and use a three-part algebraic framework to prove a function is continuous at a specific point. To prove continuity at a point x equals c, a function must satisfy three specific requirements. First, the exact point, f of c, must be physically defined on the graph. There must be a coordinate anchored at that location. Second, the general limit must exist. This means as we look at the values approaching c from both the left and the right, they must be targeting the same numerical value. Third, those first two values must be equal. The destination the function is approaching must be the same coordinate where the function actually exists. By checking these three conditions, we can mathematically determine if a function remains connected or if it breaks apart at a specific coordinate. Testing continuity at x equals 4, we use the top rule since 4 is less than 6. The point g of 4 is 8, and the limit as x approaches 4 is also 8. Since these match, the function is perfectly continuous at this point. For points not on a boundary between two rules, the function behaves like a standard polynomial. The limit is found through direct substitution. Testing the boundary at x equals 6 changes the process. For check 1, we use the bottom equation due to the inclusive inequality, giving us 5. For check 2, because the algebraic rule switches here, we must calculate the left and right-sided limits separately. Pause the video and calculate these two one-sided limits using the piecewise rules provided. Approaching from the left triggers the top equation, giving 12. Approaching from the right triggers the bottom equation, giving 5. Because these two directional limits do not match, the general limit does not exist. The function fails the second requirement. This failure at the boundary shows that the two sections of the piecewise function do not meet at the same vertical level. We can conclude the proof. Because the limit failed to exist, the function is discontinuous at x equals 6, creating a jump discontinuity. The difference between our two one-sided limits mathematically created the physical gap seen here between 12 and 5. In piecewise functions, the points where domain inequalities change are the most important areas to test. To determine continuity at these boundaries, we follow a consistent sequence: identify the point, calculate directional limits, and verify all three values match. Using these three rules allows us to identify breaks in a function through calculation, providing a clear diagnosis of a function's behavior even when a graph is not available.